The Henderson-Hasselbach equation is used to determine which buffer to use in a solution at a specific pH. So we'll go through the derivation of the equation because it helps us better understand how to use it, and then also we'll talk about why we use it in the first place. At the top part of this derivation is the dissociation constant of a weak acid. The bottom portion of the equation represents the concentration of undissociated acid. The top part represents dissociated acid, and that's made up of the conjugate base and the proton. Now, if you remember, when you put a weak acid into solution, it doesn't completely dissociate. Part of it remains undissociated, and part of it does dissociate into the conjugate base and a proton. Now, taking the log of both sides of this equation, we're able to separate out the dissociated portion of this equation. If you remember also, pH is equal to the negative log of the concentration of protons. And just so you know, the P of anything is the negative log of that thing. So in this third equation, we have the log of all of these values. And so we can take the negative pH here and the negative pKa on this side. We can do a little bit of rearranging and get rid of the negative signs on each side of the equation and come up with the Henderson-Hasselbach equation, which is pH is equal to the pKa, or the negative log of the dissociation constant, plus the log of the conjugate base over the acid. The acid is a proton donor, and the base is a proton acceptor. And since the Henderson-Hasselbach equation deals with buffers, it is best when your weak acid and your conjugate base are in equal concentrations. That way, you're able to accept or donate equal amounts of protons. That way, if you have an increase in proton concentration, you're able to accept a relatively large number of protons. Or, in the opposite instance, if you have a decrease in proton concentration, you're able to donate protons to prevent a change in pH. So if your acid and your conjugate base are equal, then in this equation, that'll give you pH is equal to pKa plus the log of 1. Now the log of 1 is equal to 0. So when your acid and your conjugate base concentrations are equal, your pH is equal to your pKa. And so what this means is that buffers work best when their pH is equal to their pKa, which only happens when your acid concentration is equal to your conjugate base concentration. The reason for that is because under those circumstances you're able to absorb or donate protons depending on the circumstance and prevent a change in pH in either direction.